And let me do this. Yeah, so here's a question there. So we're gonna be doing some questions based on continuity. So we'll be doing the tutorial, or which is the exercise. So on the exercise, so let me say the exercise. On the exercises, what we're given here, they say we should determine. They say determine if the following determine if the functions following functions are continuous at the given point or points, and or intervals. So it may happen that we deal with closed interval or an open interval. So the first question that we have f of x, which is equals to 1 0 minus 1, such that x is greater than 0, such that x is equals to 0, and such that x is less than 0. And let's say we should determine this at x equals to 0. We should determine whether functions which are given here are continuous at a given point. So this is continuity at the point. We say, right? So this is continuity at the point. So I can give you a brief about continuity at the point, which is coming from definition 2.2, right? What they say on this, they say that if we're given a function, if we have a function, if we're given a function, which in this case, the function is f of x, which is f of x, and we say that this function is continuous. If this function is continuous at a point, and that point is c, right? So this point will be continuous at c if the following three conditions are met. All right, the following three conditions, if the following conditions are met or are satisfied. Usually they say satisfied. And then the first condition is that we should check f of c if it's defined. It's defined. And then secondly, we should check if the limit as x approaches c of f of x exists. In other words, when we check that this limit exists, we must check that the limit from the left hand side and the limit from the right hand side are equal. So I can just label this here. We must check that the limit from the left hand side of f of x is equal to the limit from the right hand side of f of x. You see, right? And then we say 1, 2, 3. Then the third one, we check if from this the limit as x approaches c of f of x is equal to f of c. We see, right? So this is what we're gonna be checking here. Now, when we go back to the question, on the question they said we should determine if the following functions, which I can say the following functions, we should check if the following functions are continuous at the given point or the intervals. All right. Then that was the first question. So we're gonna go now and say that first I'm gonna check f of c. So first on A, I'm gonna check f of c. Now when I check f of c, our c there is 0, right? At x being equals to 0. So I'm gonna check this. I check when x is 0, I find that the function is 0. So I'm just gonna write 0 there. You see right now. Then this should be 0. Now I check the second one. Now I must check if the limit exists. Means that I must check the limit approaching 0 from the left of f of x, which is equal to something, and also check the limit as x approaches 0 from the positive of f of x. And if they're equal, then the limit exists. If they're not equal, then it doesn't exist. You see right now. So let's go check. Approaching from the left, it should be less than 0. If we're approaching from the left, it should be less than 0. When we're approaching from the left, we get -1, and from the right, we get 1. So we see that from the left is -1, and from the right is 1. Now we have realized that, therefore, we have realized that the limit as x approaches 0 of f of x does not exist. You see right now. But we must state why doesn't it exist. You see right now. Since we checked that the limit as x approaches 0 from the left of f of x is not equal to the limit as x approaches 0 from the positive of f of x. And then we're done with checking that. Then we come on the third point. We realize that the limit as x approaches 0 of f of x cannot be equal to f of 0. You see right now? Because this one does not exist. We see right now. Hence, I'm going to state that f of x is not continuous. This is not continuous at x being equal to 0. We see right. It is not continuous at x equals to 0. And we have stated why. You see. Then we come to the second question. The second question that we are given that they say, on the second one, they say f of x is equal to, here we have x squared minus 2x, we have 1, we have x squared minus 6x plus 4. And then here we have that x is less than 2, and here we have that x is equal to 2, and here we have that x is greater than 2. We see right. And then, now they say that we must check whether it's continuous at x being equal to 2. You see right. And then we're going to do the same thing. First, we check, number 1, check f of 2. We realize that when f is 2, and when x is 2, we get 1. You see right. Then we check the second one. We check, now we say that, check the limit if it exists, and then we check the limit as x approaches 2 from the left of f of x. When this is approaching 2 from the left, it's this one, right? X less than 2. So it means that this is the limit as x approaches 2 from the left of x squared minus 2x. And here I just plug. You see right, this is 2 squared minus 2 times 2. And this will be 0. I'm sure we agree with this. And then, now, we check the limit from the right. We say that the limit as x approaches 2 from the positive of f of x is equal to the limit as x approaches 2 from the positive. What is our f of x here? From the positive, x squared minus 6x. This is x squared minus 6x plus 4. Then I just plug. This is 2 squared minus 6 times 2 plus 4. And then 4 plus 4 is 8. 8 minus 12 is minus 4. Now we realize that from the left and right we got different values. So it means that therefore the limit as x approaches 2 of f of x does not exist. Since the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of f of x. Now, we come to the third point. Given that that limit does not exist, it means that this limit of f of x as x approaches 2 cannot be equals to f of 2. You say right. Hence, f of x is not continuous at x equals to 2. We say right. Whereas that is not continuous there. Then we have the third one. The third one, we have the third question. This one, you're going to do it as an exercise just to test what we've been doing there. For an exercise, I want you to check if we're given this. If we're given that g of x is equals to, here we have x squared, we have 2, and we have root of x minus 1. And this is x less than 0, x equals to 0, x greater than 0. Check this at x equals to 0. Right? Then we come to 4. 4, we have that g of x is, and we have 1, x over 2, and we have root of x. Now, when it's 1, x is less or equals to minus 2, and when it's x over 2, x is in between minus 2 and 4, and when it's root of x, this will be 4 less or equals to x. X should be greater or equals to 4. We agree, right? Then they say here we must check at x equals to minus 2, and the interval must also check at this interval 2, 4. We'll say right. And then now what you're going to do first, we're going to check as usual. We're going to check the first one at x equals to 2. In other words, here we're checking continuity at the point, then here we'll check continuity at a closed interval. So checking continuity at the point. So checking continuity at the point. First, we're going to check f of minus 2. We say that f of minus 2, when x is minus 2, we get 1. Here it's when x is equal to minus 2. You say right now. Then secondly, we check the limit of minus 2 when you're approaching from the left. Then when we are approaching from the left, right, minus 2, it's also this. You see, x is less than minus 2. And then, yeah, this is just going to be minus 1. It's just going to be 1. And then we check as x approaches minus 2 from the positive of f of x, this will be equal to the limit as x approaches minus 2 from the positive, which is approaching minus 2 from the positive is this, which is x over 2, which this will be equal to minus 2 over 2, which is minus 1. We agree, right? Then we realize that the limit from the left and right, they are not equal. We say, right, the limit from the left and the right are not equal. Therefore, we're going to come and say, therefore, limit as x approaches minus 2 of f of x does not exist. You say, right, this limit does not exist since must specify y. The limit as x approaches minus 2 from the left of f of x is not equal to the limit as x approaches minus 2 from the positive of f of x. Then we check the third point. The third point, we're going to say the limit as x approaches minus 2 of f of x cannot be equals to f of minus 2 because they're not equal. Because this does not exist, right? So they can't be equal. We come and say hence, was this f of x or g of x? It was supposed to be g of x. G of x. It's supposed to be g of x. G of x. Yeah, hence g of x is not continuous. This is not continuous at x equals to minus 2. Then we check the closed interval part. Now they say that we must also check whether it is continuous at the closed interval. Now, for the closed interval, I'm also going to share the definition of a closed interval. What do we mean when we say that we're dealing with a closed interval, right? And then this closed interval is coming from, on your guide, it's coming from definition 2.4. We say, right? So here, we're given a function, right? We're given a function over some certain interval. Right? We say that a function, we're going to say that a function is a continuous over, this should be over some point, right? Or let me say a function f. Yeah, let me just call it a function f. A function f is continuous. So we're going to say that it is continuous in the closed interval. Not to say over. We can say that this is continuous in the closed interval, and that interval is AB. If here it should open if all the following conditions are met. If all the following conditions are met or satisfied, right? If all the following conditions are met or satisfied, or they hold. So the first condition should be f is continuous at every point. So it should be continuous in the open interval within this. Every point within this open interval should be, within this interval, it should be continuous. So this is continuous at every, this should be every x in the interval, in the interval AB. It's right then. This should be continuous in the interval AB. And then we check 2. And then now for the second one, we're going to say that f of A and f of B both exist. Then there we're just gonna be checking f of A, f of B. We're just gonna be checking the left hand limit and the right hand limit, right? And that means that for this one, we're going to say that the limit as x approaches A from the positive of f of x. So we check the right hand limit. We say that this is of f of x. The right hand limit, if it's equals to f of A, then this should be right continuous. You say right now. And if the left hand limit, x approaches A from the left of f of x is equals to f of B, then this should be continuous in the left hand limit. And then we know what to say, right? And then we come now to do B. Now with B, with this one of 2, 4, now we're going to say that for me to check here that this g of x is continuous in this closed interval, I'm going to first have to check the open interval. Is that right? It means that I'm going to say first I'm going to say, let me say Roman figure 1. Then I first check that for every, remember, it says that for every x in the interval, what is that interval here? 2, 4 should be the open interval. For every this g is defined. You see, right? We realize that g is defined by, so we say g of x. We're going to check what is it defined with by. Right? We're going to check this interval 2 to 4 should be the open interval. 2 to 4, 2 lies within here. You see, 2 is within this. We've learned from formal definition that we are allowed to do something like this, right? 2 lies within this interval. You see, right? So it lies, or it is defined by x over 2. You see, so since 2 lies within that interval, then we can now go up and say that this is defined by x over 2. You see, right? So the g is defined by this, so we can use this to check whether there is continuous in the open interval. So now within that we check the limit as x approaches c of g of x. Within that interval we find that this will be the limit as x approaches c of c over 2, which is this, not of c over 2, of x over 2, because that is x over 2, which this will be c over 2. And then now we check g of c. G of c will also be c over 2. Now we realize that the limit as x approaches c of g of x is equal to g of c, which is equal to c over 2. You see, right? Hence, g of x is continuous. So I can say that this is continuous. I can say that this is continuous at every point. So C represents every point there right now. Continuous at every point in the interval. 2 till 4. You see, right? So this will be continuous in that interval from 2 till 4. And then we come to the second one. Now we have checked within the open interval. Now we must check f of a, f of b, if they both exist. You see, right? So f of a in this case, it will be f of 2, and you see f of a, then f of b. So we check f of 2, f of b, f of 4, f of 2, f of 4. And then now we check. Now this will be g, since we're dealing with g, we check g of 2, which g of 2 will be equal to, we go back to check where x is equal to 2. X is equal to 2 within here. We agree, right? X is equal to 2 here. So we can go and say this will be 2 over 2, which is equal to 1. You see, right? And then we check g of 4. We check where 4 is equal to, that it's where it's x is equal to 4, where we have root of x. So we're going to say this will be root of 4, which is equal to 2. We agree, right? Then now we know that we can come and say, we know that g of 2 and g of 4 are defined. You come and say, therefore, g of 2, and on instead of g of 2, we can also say that, therefore, g of x is defined at x equals to 2 and x equals to 4. We see, right? We have checked if it's defined. Now we check the right hand limit. We also check the left hand limit. Then we equate them to our f of a and f of b. So let's check the right hand limit. The right hand limit, we're just going to check the limit as x approaches 2 from the positive of g of x, which this will be equal to the limit as x approaches 2 from the positive. We're going to check which function is greater than x, where x is greater than 2. X is greater than 2 here. You say right, x over 2. Then, because 2 is within here, we agree right now. So x is greater than 2 there. You see? So we check that. And this will be x greater than 2 there on x over 2. This will be 2 over 2. This will give us 1. We realize that the right-hand limit, come and say, therefore, limit as x approaches 2 from the positive of g of x is equals to f of 2. You're not f of 2, g of 2. You see, right? This is equals to that. Hence, g of x is continuous at x, so not just continuous, is right continuous. Is right continuous. Is right continuous. This is right continuous at x equals to 2. Then we check the left-hand limit, which is the limit as x approaches 4 from the left of g of x. We go check which one is approaching 4 from the left. There. We go check which one is approaching 4 from the left. We realize that the one which is approaching where x is less than 4, it's this one. Still this one, right? X over 2. Then we're just going to use it. And then that will be x over 2, which this is equals to 4 over 2, which is equals to 2. On that we had got 2 also. Then we say, therefore, the limit as x approaches 4 from the left of g of x is equals to the limit, not the limit, man. It's equals to g of 2. G of 4, not 2. G of 4, which is equals to 2. This one I should have said also equals to 1. Alright. Now I can come in and say, hence, g of x is left continuous at x equals to 4. This is left continuous at x equals to 4. Then now I must conclude, right? I must come with a conclusion. So I've checked that it's continuous, left continuous and also right continuous. So now I must come and have a conclusion. Now on the conclusion, I'm going to say that g of x is a continuous, or you say that g is continuous at or over 2, 4, close the interval. If it was left continuous, right, let me show you something. This is called right continuous because it's facing right. So that's how I remember it, right? Right continuous, it's facing right. This is a left continuous. So when they're both continuous, we're just going to represent it like this. You see, right? But when one, if 2 is left, not if 2, if 2 is right continuous, let's say if G is right continuous and not left continuous, then we represent it like this. You see right now? And then if G is not right continuous and is left continuous, then we represent it like this. It's not right continuous, so it will have this. It's left continuous. You see, the bracket facing the left will be like that. So we're going to check like this, right? If it is not left continuous and right continuous, we are just going to do this. Because there is continuous within this interval, but it is not continuous at the endpoints. You see, but this one we found out that it is continuous in here and here. That's why I had to represent it like that. And then from here, you can try to do number 5, which number 5 is as follows. You can do this one as an exercise, not to make the let me say an exercise, not to make the recording to be too long. We can have this as an exercise. This one says that f of x is equals to, this will be 2x plus 1, 3x, 2x minus 1. Here we have x is less or equals to minus 1. We have that minus 1, x, 1. Here we have x greater than 1. We must check this at x equals to minus 1 and also and in the interval 1, 4. Make sure you write this.